Hello, welcome to Solved Papers channel. I'm Godfrey. In this video, I'm working cab range A2 physics questions. Topic here is oscillation. This is a 2019 June exam series coverage. Let me say this before we get started. I encourage you, as you do your revision, consider topic-wise revision. Read a given topic, and when the content of that topic is fresh in your mind, get topical questions on that topic and attempt them. In this way, you will be able to know which are the key areas examiners are fond of frequently setting. And I encourage you to do as many topical questions for different years: 2019, November, 2019, June, 2018, 2017, and so on and so forth. This way you are sure to get exposed on all the areas that given topic has been tested over the years, and that will make you prepare adequately. I'm sure you're looking forward to get your A-star. You get a good grade, this will open for you the university doors magically. Once you're done with the topical questions, then you can resort into attempting past paper, full past paper questions. Of course, this will be necessary as you time yourself and build speed. Past papers in physics, past papers in A2 are usually 2 hours. Approximately, you usually have 12 questions. Therefore, in 2 hours, you should be able to finish to complete those 12 questions if you build speed, look at topic questions, and also resorting into doing past papers. I guarantee you, in this way, you will get a very good, encouraging grade. If you have not already subscribed to my channel, please click the subscribe button and hit the bell icon. This way, you will be notified every time I upload a new video. Shall we get started? Question number 1 was set on variant 4.1, and this was question number 3. These questions are on oscillation. So let's get started. In number 1, we are told a hollow tube sealed at one end has a cross-sectional area A of 24 centimeters squared. The tube contains sand, as you can see right here. It has sand inside, so that the total mass M of the tube and the sand is 0.23, the total mass of the sand and the tube. The tube floats upright in a liquid of density rho, as illustrated. This is a liquid, and of course part of the tube is immersed in the liquid whose density is rho, right there. The depth of the bottom of the tube below the surface is h. The tube is displaced vertically and then released. The variation with time t of depth h is shown as it is in this case. You have h on the y-axis, and time is always on the x-axis. This is a fig 3.2. Question 1, part A, we are taught to determine the amplitude in meters of the oscillation, right? Okay, so you come to the graph, the amplitude of the oscillation, which happens to be constant. Of course, you find the midpoint of the equilibrium position of this graph. The equilibrium position of this graph is this point here at 4. If you draw a line at 4, that is the equilibrium position of this graph. This is the equilibrium position of the graph. Therefore, you can see the amplitude is this distance here. Let me get red. The amplitude is distance from there to there. That is the amplitude. Therefore, the amplitude is basically 6 minus 4, which is going to be 2 centimeters. That is the amplitude. So the amplitude here, amplitude is equals to 6 minus 4, which is going to be 2 centimeters. This is minus, and of course the amplitude is in meters, so you change these 2 centimeters into meters, which will be 2 times centi is 10 raised to power minus 2 meters. So this will be 2 times 10 raised to power minus 2 meters, or you can just write 0.2 meters, so 0.02 meters. I've said that you can still write 10 raised to power minus 2 meters to still be correct. Frequency of the oscillation of the tube in the liquid. So to get the frequency of the oscillation of the tube, we need to get the period. We go back to the graph. The period is one complete oscillation. One complete oscillation is from there to there. There is one complete oscillation. I'll go for that. You can go for whichever. It doesn't matter. You can also go from here to here, but I'll go from here because we have this values here given. So the oscillation is t is equals to 1.2 minus 0.6, which is going to be 0.6 seconds. The oscillation is 0.6 oscillation right there. Okay, so once you know the period, then we know that frequency is equals to 1 over t, and we found t to be 0.6, so this is going to be 1 divided by 0.6 seconds, 0.6 seconds, and this will give you 1.7 hertz. Of course, if you do calculation, you get 1.66 hertz. Of course, 1.66 hertz will be 1.7 hertz. So 1.7 right there, hertz. You're taught to find the acceleration of the tube when h is maximum. Of course, acceleration for oscillating objects, acceleration is equals to minus omega squared x. Right? We know that omega is 2 pi f, and we can get that 2 pi f times frequency is 1.7, and this will give us 10.68 radians per second. We have gotten that, so now we can calculate acceleration. Maximum height is 0.2. We had found that, so this is going to be minus 10.68 squared times x. Maximum is 0.02. We had calculated that, so when you calculate nicely, you're going to get acceleration of 2.28 meters per second squared. We have calculated acceleration. Therefore, this will be basically 2.3, close to 2 decimal point. 2.3 is the answer there. Part B, the frequency f of the oscillation of the tube is given by the expression f is equals to 1 over 2 pi square root of cross-sectional area times density times g divided by mass, where g is the acceleration of free fall. Calculate the density of the liquid in which the tube is floating. Of course, you need to make raw subject. To make raw subject, you need first to remove the square root. So you multiply by 2. You square by 2. Of course, you're supposed to multiply by 2 because square root is basically a half. So you need to multiply that to remove it. multiplied by 2, so this will be 1 over 4 pi squared. So this will be times A rho g over mass. Therefore, we need density, so we make density subject. Density will be 4 pi squared, frequency squared, times mass. Of course, you multiply both sides by this, divide by, of course, cross-sectional area times g. Cross-sectional area times g. You substitute here the values of this is 4 times frequency is what you've gotten up there. Frequency is 1.67 squared. We are told the mass of the sand and the tube is 0.23. 0.23. All of this is divided by cross-sectional area, which are given as 24 centimeters squared. So this will be 24 times 10 raised to power minus 4. And G is 9.81. Correct evaluation will give you 1076 kilogram per meter cubed. 1076, approximately 1000, which is the density of water. That's the density there. C, the oscillation illustrated in Fig 3.2 are undamped. In practice, the liquid does cause light damping. On Fig 3.2, draw a line to show light damping of oscillations for t is equals to 0 to t is equals to 1.4. Damping, the amplitude reduces with time. So here we are. We can erase this. So damping, when this liquid is damped, the frequency will remain the same. But the amplitude will decrease. So I can draw something like this. Light damping. Up to here. Something like that. So the red line is when there's light damping. Yeah, that's it. That's what you needed to draw. Before we go to question number 2, let me say it's great you're watching this video. Remember, practice makes perfect. I encourage you to practice working out these questions yourself as I guide you. You don't just watch. Look for the for the topical question of these questions and attempt them yourself. This way you will get the most of what I'm trying to show you here. You may get this same paper and many more from solvedpapers.co.uk. The site that I'm talking about here is this site here, this solvedpapers.co.uk. You might get the papers from this site, and all you need to do is get to A level. Of course, we are doing physics 2019. You go to A2 questions right there. You'll come to this page. Of course, you'll find there are both November and June physics A2 topical questions for 2019. The question that we are dealing with is now oscillations June. This question, this topical question here. So I need you to get it. Of course, you can get the rest, all these other topical questions, by coming right here on this green button. You click that, you will come to this page. Of course, we are on 2019. You can go to 2019 right here. We are dealing with June. So you come down here to June, and you may ask your parents to help you acquire these papers. They are basically only £10. You need to click here and proceed to check out. I encourage you to get even November 2019, 2018, November, June 2017, November, June, and 2016, and attempt as many topical questions. I've taken into account that these papers are arranged topic-wise, and that is a good thing. You do as many topical questions as you can, you are setting yourself up to succeed. You may also get all the papers at a discount when you come here. Of course, you can get them at a discount: physics, chemistry, and mathematics A-level, A2, for both all the years up to 2016, right there. While at it, let me also say that I also help students online. So I have online tuition classes. If you need my assistance, I'm available at spacademy.co.uk. This is the site I'm talking about here, SP Academy. This is the site. Of course, you may take time to explore the site. The courses offered are ICT, mathematics, physics, biology, and chemistry. I need you to have a look at the step-by-step student guide by clicking here. You may also click here to watch a video and get familiar with the online live classes. Of course, if you're a tutor, then I need you to go there. Of course, once you make up your mind that you need my assistance or assistance from my other colleagues, then I need you to register here. Of course, you get us your name and give us the correct email address. We will send you an email which you require to click to activate your account. Once your account is activated, you need to sign in and then come here and find a tutor. And hopefully, I will have you in my class. So I welcome you in my classes. Let's do this and help you get your A star. That way everybody will be happy. So I charge a minimal fee. If it's one-on-one student, I'll charge you 35 pounds per hour. Very minimal charges. If you come with your 3 friends or even 4 friends, I'll give you a discounted price of 25 pounds per hour minimally. And let's do this and help you guys get your A stars, and this will open your university doors. You will not need to be worried which university will go, as long as you get your A star, or the university will be looking out for you. Right, on with question number 2, which was set on variant 4.2, and this was question number 3, May-June 2019. All right. So question number 2, a spring is hung vertically from a fixed point. A mass M is hung from the other end of the spring, as illustrated in Fig 3.1, right there. The mass is displaced downwards and then released. The subsequent motion of the mass is symbol-harmonic motion, as indicated by the graph here. Variation with time t of the length L of the spring is given in this Fig 3.2. Length on the y-axis, time on the x-axis, as you can see there. State, that is part A, state one time at which the mass is moving with maximum speed. Maximum speed is when the mass is at equilibrium position. This is the equilibrium position. If you draw a line through here, this is the equilibrium position. At equilibrium position, the density is greatest. At extreme ends of the oscillation, velocity is 0. But here, velocity is max. So you're supposed to find any one of these points where the speed is maximum. So you can look at that point there. This is 0.1. This point here. This is 0.3. This point there. This is 0.5. This point there. is 0.7, this point here, this is 0.9. So all those points, the speed is maximum. So speed is maximum at equilibrium. That is what I'm trying to point out to you. So speed is maximum. Speed is maximum at equilibrium position, and those equilibrium positions are, as I've indicated there, they happen to be odd numbers. So the equilibrium position, the timing will be 0.1, 0.3, 0.5, 0.7, 0.9. So you can choose any one of those. I'll go for 0.1 to still do. State the time at which the spring has maximum elastic potential energy. Maximum elastic potential energy is when the spring is stretched. When it is stretched and released. Those points where it is stretched, that is when it has maximum elastic potential energy. So I'll go for t is equals to 0. Other times, so we'll have maximum elastic potential energy at 0 seconds. We'll also have it at 0.4 seconds. We'll also have it at 0.8 seconds. I can show you that in the graph here. So at this point, this is when it is stretched, right? So this is at t is equals to 0. And then, of course, at this point here, this is when it is quotient, when it comes up. So that is not maximum elastic potential energy. So this point here again, 0.4. And this point here again, 0.8, this point here, 0.8. At this point, 0.6 and 0.2, it has got the least elastic potential energy because it is, the spring is quashed. So having that in mind, you can choose any one of the timing. I can just go for 0.4 seconds. That is the time the spring has the maximum elastic potential energy. B, we are taught to use the data from Fig 3.2 to determine for the motion of the mass the angular frequency, omega, the angular frequency. We know that angular frequency is 2 pi upon t, right? Or 2 pi f, whichever one you have. But you can get t. T is the period from the graph. You can get t from the graph. Let me do away with all this. You can get t from the graph. Period. So I'll go for this. Also from 0 to this. So basically t is 0.4. So also from there to there. So it will be 0.8 minus 0.4, which gives us 0.4. So period is 0.4. So we come here. We have found that period is 0.4. Therefore, our angular frequency is 2 pi over 0.4. And good calculations will give you 15.7, which is approximately 16 radians per second. That is angular velocity. So 16. Maximum speed. Maximum speed is, you say that it is at equilibrium position. So V naught is equals to omega times the displacement there. So the displacement, angular velocity we found is angular frequency. We found is 15.7 times the speed, the x naught, which is 2.5 centimeters. So of course you convert the centimeters to meters. So what you get is 0.39, 0.39 meters per second. So 0.39 meters per second. The magnitude of the maximum acceleration. Of course, acceleration, maximum acceleration, let's say is a0, is equals to omega naught squared x naught. Remember, this is a angular velocity, simple harmonic motion, and of course omega is 15.7 squared times the displacement, which is 2.5 times 10 raised to power minus 2. When you do correct evaluation, get the maximum acceleration is 6.2 meters per second squared. 6.2 right there. Okay. Part C. The mass M is now suspended from two springs, each identical to that one of Fig 3.1, shown in this 3.3 here. Suggest and explain the change that will be noticed in this one here. So the period will be, because the two springs will have a higher spring constant, that is, the stiffness will have increased, and therefore the period T is now slow. Of course, is now shorter. Right, than 0.4. Now, if that is the case, then the restorative force is greater for any extension. Of course, when the spring constant increases, force is also going to increase. Don't forget, force is equals to spring constant times extension. Therefore, extension now has increased, and therefore, for any extension, force will have also, the restorative force will have increased, and for any extension, and thus acceleration, because you are supposed to explain the change in any in the period of the oscillation. Of course, we don't need a numerical answer. Thus acceleration is greater. Don't forget, force is equals to acceleration times mass, and therefore acceleration is equals to force over mass. Of course, when the force increases, because in this acceleration is directly proportional to force, when force increases, acceleration increases, is greater, meaning maximum speed is higher. Sorry, maximum speed is higher. So you are supposed to explain change in period of the mass period. So the period will be, we've said that period will be, the period is now shorter. Period is now shorter. There we are. Let's go to question number 3. Question number 3. I was set on paper 4.2. This was question number 3. Okay. Cylindrical tube sealed at one end has cross-sectional area A and contains some sand. The total mass of the tube and the sand is M. The tube floats upright in a liquid of density ρ, illustrated in Fig 3.1. The tube is pushed a short distance into the liquid and then released. State the two forces that act on the tube immediately after it is released. Of course, there is the upthrust due to the displaced water, and of course the weight of the tube. So the two forces, one is upthrust. State the two forces. Of course, you don't need to explain, but I can explain where the upthrust is coming from due to the displaced water, displaced volume of water. And then we have the weight. Of course, weight in this case, since we are told the mass is m, the weight will be the mass times g. That will be the weight of the tube right there. The weight. Those are the two forces, upthrust and weight. State and explain. Don't forget, those are two questions. State and explain the direction of the resultant force acting on the tube immediately after it's released. Of course, the resultant force will be up because after the tube has been pushed downwards, then once you release it, it will come up. So the resultant force is upwards. Okay, let's explain that. Of course, since there are two forces acting, it means that the upthrust will be greater than the weight. So in this case, the upthrust is greater than the force, so than the weight. Sorry, the upthrust is greater than weight of the tube. There you are. B. Acceleration of the tube is given by this expression. A is equals to a rho g over m x, where x is the vertical displacement of the tube from its equilibrium position. Use the expression to explain why the tube undergoes simple harmonic motion or simple harmonic oscillation in the liquid. You can notice that the quantities a rho g over m are all constants, and this is same as angular frequency omega. So acceleration is proportional to displacement. So you can say the quantities a, rho, g, and m are all constants. Okay, therefore acceleration of the tube is proportional to displacement. Right, that's why I say A is proportional to negative displacement. So this is the condition that this is the condition that when satisfied, then the object is usually undergoes a simple harmonic oscillation. All right. For the tube having a cross-sectional area of 4.5 centimeters squared and a total mass of 1.7 kilogram, the period of the oscillation is 1.3 seconds. Determine the angular frequency omega of the oscillation. Of course, we know that omega is equals to 2 pi over t, right? Or omega is 2 pi f. We are given t here, so you can use this one. Say 2 pi over 1.3 seconds. Correct evaluation will give us 4.83 radians per second. That is angular frequency. 4.83. So I can just give it in 2SF, which is because all the values are given in 2SF. This is 2SF, this is 2SF, so the answer should also be 2SF, so that the answer doesn't seem more correct than the raw data. Use your answers in part 2 and part 1, this one, and the expression in B to determine the density of the liquid in which the tube is floating. Of course, the expression here is this one here, right? You can make raw subject from here. We need raw, so raw will be acceleration times mass over acceleration times mass over air times g. So that is the expression there. So density is equals to air times m over cross-sectional area times gravity times actually times x. I've not mixed out here. It's times x. Yeah, this x here. This is times x there. So this x there times x. So I can write this one as gx, cross-sectional area times g times x. Therefore, air is basically what you have the acceleration, but remember air rho g over m, this is omega squared, and of course using this you can substitute this value. You can substitute this value right here. You can substitute this value right here. Therefore, our rho will become, this is rho, this is rho, so this rho here. So therefore we can substitute this right here, because we know that A is omega squared x. So the omega squared here is arrow, yeah, arrow that, and we need density. So you can also actually say omega squared is equals to rho g over m, and of course we can make density here as density is omega squared times mass over g. Yeah, this is the correct one. This one we need a and we need x. We can simplify it to this. So this equation here, we can do away with this one. We can do away with this one, and then write density is, rho is equals to omega squared m over g. This will give us, omega is what you have calculated here. So 4.83 squared times mass, which you're given up there as 0.17. This is cross-sectional area. You're given as 4.5. 4.5. I can show you that here. Cross-sectional area. Where is that? Is the cross-sectional area? Where is the cross-sectional area? Yeah, given it here. Given the cross-sectional area centimeters. So 4.5 centimeters squared. This is the same as 4.5 times 10 raised to power 2. Since it's the centimeter squared, centimeter squared basically means that. So you square this, this will be meter squared. So what you get is 4.5 times 10 raised to the power 4 meters squared. So that is what you're going to use here, 4.5 times 10 raised to the power 4 times G, which is 9.81. 9.81. Good evaluation will give you rho is 900, and this is the unit of density, meters per centimeter cubed, which is given here, 900 kilogram meters cubed. Great. That is the end of this topic. This topical question. Get more topical questions from this site, solvedpapers.co.uk. You need my help, you know where to get me, spacademy.co.uk. Hopefully I'll see you in my next video. Cheers, guys.